Hello, hello, Colin.
Morning.
Good morning. Hello, Brittany. Hello, Judith. Hello, Alexis. Or I should say, good morning. Um, Chat. One sec. Oh, okay. Sorry. Good morning, Gaia. Good morning, Judith. Good morning, Ryan. Good morning, Alexis. There's Xavier. Xavier, did I say Brittany? Good morning, Brittany. Or you did? Oh, you put. Oh, that's John. Okay, okay. Good morning, Chanel, who's here very early. Thank you. And good morning, Emily and Anissa and Ethan. Okay. Oh, okay. We are just gonna get rolling. So some of you have gotten exams back. Some of you have not. They're just coming. I apologize. They're still coming. They're just coming slowly, but they're happening. So if you haven't gotten one back yet, it means nothing. But it's just where you're falling in the alphabet of all my classes or something like that. Um, and I apologize again, but they're just coming. Like just yours will drop. Whoever you are, it will drop into your box at some point. It's not like I'm waiting for next class, and I apologize, but they are coming, and they're good so far for what it's worth. I mean, I don't want to get into a whole, but so far, I'm actually pleased, but I just don't want to go down that rabbit hole now. And I know you're not pleased with me or the situation, but they're coming and they're coming. Um, uh, all right, so we're just going to keep going. Well, oh, and sorry, and good morning, Ariana. And obviously, if you have any questions or if you're freaked out in any way, the other thing, just a quick side note, because it's this point in the semester, and I know not having something back can cause anxiety. Just even though I'm telling, even though I'm saying it's not personal and all of that, and you have and all of that. If it's freaking you out in any way, or you just like want more information, or you're like, I need assurance, or just like anything, just text me or email me and say I would just like a 15-minute phone call just to ground myself, or to know what's or so, or can you take a quick glance at my, even if you're not up to my exam yet, can you take a quick glance at it while I'm on the phone with you? And I can do that. I mean, I'm not saying you need to, but I get it. So feel free or come by tomorrow at 11 a.m., etc. All right. Anyway, um, um, a lot of people come. Sorry. Wait, there's a lot of people. Waiting. Okay. And whatever I just said, please pass on to your colleagues if they're showing up now, because I don't want to rabbit hole the whole class about it. But now what I want to do today in terms of material is move on to sort of like the last big topic of this semester. It's not big, but the last whatever. And the thing that the homework that's due Wednesday is about, I may extend that. Let me look at that again. Hold on a second. I know there's homework due Wednesday, and I know I continue to be behind. So let me look for a second if um oh, next week is May 5th. Yeah, I don't I'm gonna start dealing with it today. So I'm telling you the homework that's due Wednesday. Let's just be flexible about it. I'm not going to change the date because we're going to get backed up with other things, but it's not as bad as it looks, and I'm going to try to help you with a lot of it right now. Um, but but if it comes in late, I won't, I won't lose sleep over it, and neither should you. But just there's a couple more that come in. So anyway, so the topic that I want to introduce today is the topic of these next couple of homeworks. Um, where did you just go? Okay, I hear you, direct chat person, and good morning, Nasreen. No problem, no problem. But I want to ask you quickly before I move forward. Um, what I was trying to help last week was on the good morning. Um, you know, what I was trying to do last week was do sort of what I think. is a problem that combines all of the most challenging subtleties of Newton's laws. That is, it combined an angle with friction, with an unexpected result, and hopefully was helping you with your lab. That was the point of last week. But here's my question. Oh, right, right. Direct chat person. I'm amazed you're here at all. No problem, direct chat person. Got you. Thank you. And good luck. What I'm trying to say, that what I was trying to do last week was, help you with the physics, but specifically with your lab report. So I want to ask before I press forward, please remind me again, your lab report for lab 5, that was that due, that's due this Wednesday? Is that correct? I keep getting your days, or is that due this? I keep getting your lab date confused, but is that due, like, when is that due? Or what, or did you turn it in last week? The formal lab report for lab 5, the slow down lab. Did you turn uh, post lab? Thank you, Colin. Or the post, which means that the formal lab still isn't for a little while. I mean, I hope they're not. I hope you do have a. I mean, the post.
Yeah, I think she pushed it back.
Okay, which is fine. Great. Okay, which is fine as long as it sort of let me know if she totally cancels it, and I won't. Which she shouldn't. I mean, that's one lab report that should not be canceled. But okay, she pushed it back. All right, then, and I'm sorry too. I'm losing my mind. In your case, it's Walters or it's Mercedes. It's Hema or it's Mercedes for your section of 203.
Mercedes.
Mercedes. Okay. 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 Thank you. So here's my quick question. And I'm not trying to make you guys jittery. I'm just always jittery. My question is there any questions that you guys have is about anything I was saying last Wednesday regarding down, up, anything I was saying at all, about the diagrams or the conclusion or the analysis or anything further that I can say to help you with lab 5? And again, and by the way, again, just sort of sidebar, often there is a problem that's sort of very similar to or relate. There's often an inclined plane on the final exam. So this is all not, just like in the abstract. I kind of really want to make sure you're okay with inclined planes. So if there's any question at all now about anything I said or anything I didn't say regarding the general physics of inclined planes or the lab, I would love to hear it right now. I'm looking in the chat. So I'm going to pause for a second. And I'm saying, like, because I'm kind of going to move on otherwise, and I'm not 100%. I don't feel 100% secure about doing that. So I'd like to know if there's any concerns or questions or about inclined planes, friction, the lab. I'll pause for a second. Okay. And if something occurs to you, even once I get rolling on the other topic, if something occurs to you, please do feel free to bring it up. I mean, my summary again, I mean, I'm assuming that you all, or that most of your data showed that the thing takes less time to go up an inclined plane than it takes to go down. And I'm assuming that that's slightly surprising, or that most of us would not expect that. Like I definitely would not expect that. Um, and yeah, and so the sort of the ultimate point of the lab is to explain why it actually makes sense once we think it through, that it's not, that it's maybe a surprise, but it's not an accident. And my ultimate explanation, right, just to summarize again, is that I think the net force on it has, again, one huge thing is it has nothing to do with the initial velocity of the ball. It has nothing to do with the fact that you flick the ball up. You really need to understand that. What it has everything to do with is that the net force acting on the ball while it's on its way up is greater in magnitude than the net force acting on the ball on its way down. Because on its way up, the forces are acting together in the same direction, whereas on the way down, the forces are in conflict. So the net force is greater on the way up, which means the magnitude of acceleration is greater on the way up than it is down. The magnitude of acceleration. What that then means in English, or since it is absolutely true that on the way up, the thing is accelerating in the opposite direction from the way it's moving, whereas that's not the case on the way down. On the way up, the ball is losing speed. On the way down, it's gaining speed, but it loses speed at a greater rate on the way up than it gains back that speed on the way down. So it loses speed until it gets to zero speed, and then it starts gaining speed on the way back down, and it never gains back all the original speed that it had when it started at the bottom. It never gains, right? It never gains back the entirety of the speed with which the entire round trip started. Therefore, on average, it goes faster on the way up than it does on the way down. Like it's not a trick. It literally moves faster on average on the way up than on the way down. Even though, or in fact, because all the forces are working against it together on the way up. Like if you see that in your mind, you see a lot, I think, about physics, and you're in good shape to write your lab report. If you don't, you should ask me. And last thing, if you really see what I just said, well, first of all, then that shows that you're really on the road in physics because you're really seeing the difference between acceleration and velocity, right? That you could be slowing down but still be going fast on average. That's kind of what we're saying, right? And also, then you really see why the initial velocity of the whole thing, your flick, doesn't matter at all. Like it has to be there for the phenomenon to for the lab to occur. You have to flick it somewhat, but whatever speed you flick it, what we're arguing is whatever speed you flick it is fine. Like the faster you flick it, the higher up this trip will be. That's fine. But at the end of the day, no matter what you do, the ball is not going to get back to your original flick. It's not going to regain all the speed that you initially gave it. So it's like V naught to zero and then zero to something less than V naught. That, okay. So if, okay, but I'm, so going once, so we're okay with like, can I just see thumbs up if we're like okay with that and I can move on? I should move on. Okay, okay, that's good. Thank you, Colin. Thank you, Carolina. Thank you, Michaela. Okay. Okay. Oh, sorry. And I see others. Thank you, Xavier. Thank you, Judith. There's that guy. Thank you, Anissa. Thank you, Ariana. Okay. Thank you, Adenelsi. Okay. Okay. Um, then I'm going to move. All right. Then let's move on. So now, new topic, new subtopic relevant to the next homeworks. The equations I'm about to develop are the ones that I just flicked past. Like my the equations that were just on the board, you have not seen before from me. My point is that now I'm going to develop them for you. So the new topic is a topic of called work in physics. Okay. Um, excuse me. Okay, so what I'm saying, so we're the top, I'm just switching the views. The topic is work, and we're going to build the idea of work sort of in stages. We're going to go from like the simplest possible case to more elaborate cases. So so in the first case I want you to consider of work, I want you to sort of restrict it in two ways. One, consider a very small amount of displacement, and then two, consider a force that is along the same axis as that displacement. So we're going to push or pull something through a space, right? Like this. Oops, sorry. Okay, in this, okay, so we're just like we got a box on the floor and we're pushing it across the floor. Some small but finite amount of displacement, delta x, or I should say distance, delta x. Okay, then if we do this, oh, and the force, of course, is measured in newtons, and the displacement is measured in meters. Okay, under these conditions, we're going to define work to be the work done on the box to be the force multiplied by the displacement. That's it. Okay. Now I'm saying triple equal sign because I'm giving a definition, but I'm making them squiggly because I'm saying this is not really the definition of work. This is the definition of work in this simple case. By simple, I mean the displacement is small and the force is parallel to the displacement. But let's just stick with this case for a couple more minutes. In this, so we're just, this is a definition. I'm not saying it's a discovery. I'm saying from here on in, if you if you push a box across the floor and you exert 5 newtons of force and you displace it for 3 meters, then you have done 15 units of work on the box. So let's talk about units for a second. Okay. Okay, so I'm trying to keep this to be a simple example, but okay, but obviously it's going to get more elaborate in a moment. But first thing I want to say is unit wise, from here on in, 1 joule is defined to 1 joule of work is defined to be 1 newton of force times 1 meter of displacement. And that is the same joule that you may recall from chemistry, as in 4.18 calories equals 1 joule. It's the same joule, and the connection is not obvious yet, but hopefully in a few minutes I'll show you what the connection is in. Um, but right now, what I'm saying is a joule is a unit of work in the MKS system, and it literally means 1 newton of force times 1 meter of displacement. Now, before I make this more elaborate, like again, this is just a definition. It's not a discovery. We're just like starting to calculate. So of course it raises the question like, why are we even doing this? Or like what good is this? The the answer is that Newton's laws are in fact not only are they super powerful, but in principle, Newton's laws are complete. Like in principle, we could end the course. I mean, we could end the course right now, and physics could have ended. The study of classical mechanics could have ended in like 1727 when Newton died, because in principle, if the goal of physics is to predict where something is going to be when, or if the goal of forensic physics is to retrodict where something was when, and again, I'm not being cute when I say those things. Like all of physics is about points of mass in points of space at points in time, and all of physics. Oh, sweet. Yes, absolutely. Direct chat person. Yes. But for real, all of physics is about knowing where things are going to be when. I mean, what the space-time coordinates are for mass points. Like that literally is the totality of physics. In classical physics, we're trying to predict the future space-time coordinates of particles. In crime-solving physics, we're trying to figure out where particles came from or when. Like no joke, right? It's like that's why you guys are required to take physics before you, especially if you were going to become criminalists. But even if you're becoming toxicologists, or anyway, you get my. So physics is all about mass in space and time. Now, in principle, if you complete Lab 5 and you sort of understand even a subtle version of a bunch of forces acting on an object, what you're supposed to take away from that is the Newtonian program that says if I know all of the forces acting on a point of mass in a point of space at a point in time, if I properly draw the free body diagram, and especially if I then make it a component diagram, and I have all these arrows arranged on axes acting on a dot, right? Like this is the new Newtonian, this is the idea of F net equals ma. If I know all the arrows acting on a dot at a dot of space and time, then I know the instantaneous acceleration of that dot, right? I know the rate of change or the rate of change of the position with respect to time of the dot, like right now at that instant. And from the acceleration, I go back to the earlier material of the course and do things like x equals 1 FAT squared or whatever. From the acceleration, I can predict the entire trajectory or retrodict the entire trajectory of the particle. So the idea is that by knowing all the forces on a pixel, if you like, or on, let's say, on a frame, on an object in a frame, in a snapshot, if you know all the arrows acting on the snapshot, then you know the key quantity to describe the object in that snapshot. You know the instantaneous acceleration, the second derivative of position with respect to time, right? And from that, you can predict the whole movie, or you know from that the whole movie of the particle. It's like saying if you know one point on a curve and you really understand how derivatives and calculus work, then you can interpolate or yeah, you can like reverse engineer the whole curve. What did I just say? Yeah, if you know the slope at a point of a curve, well, and in theory, if you know the slope of the slope and the slope of the, but if you know derivatives, you can infer the whole function. So the Newtonian program is complete in and of itself. It is a complete and powerful way to know where all particles are going to be at all points in space and time. The, but the reason physics progressed even past the Newtonian principle and developed other ideas such as this one, such as work, is that it has all the advantages and disadvantages of a pixel by pixel approach to the universe. Like, no joke. Like, the thing about Newton's laws is it allows us, but forces us to analyze one point at a time, one point of mass in one point in space at one point in time. That's the whole thing about derivatives. What's amazing is they allow us to micro focus on what's happening in an instant at a location. That is a major breakthrough. I mean, I hope you appreciate that. Um, but at the same time, that's the limitation of limits is that we're then analyzing one pixel at a time of space and time. So the next development in physics is okay, that's fine, but what if we want to zoom out? What if we want to be, is there a way we could be a little bit more efficient once we see patterns through space and time? Is there a way we can zoom out and instead of just looking at all the forces acting on a dot, free body diagram, can we start asking ourselves what's the accumulated effect of force throughout some space, or in fact, throughout some time? That's like a thing as well. Here, what we're going to look at first is the accumulated effect of force throughout an interval, like a finite interval of continuous space. Okay. So that's why we're doing it so we can zoom out. And last thing, I'll get back obviously to the, well, yeah, without at the risk of like doing a spoiler alert, what I'm really trying to argue, since you've taken calculus, right, and you're only beginning in physics 203, we're lifting the concepts of calculus and showing how they apply to the world. And then in physics 204, believe me, you have to sort of deal with them a little bit more rigorously than we are here. But to complete the thought, I'm saying the Newtonian picture, F net equals ma, and all the kinematics you did right before that, that's all a derivative picture of the world. It's how much information we can gain if we look at one derivative at a time, one point at a time. Well, what we're really about to get to now is the flip side of that. You might be seeing calculus wise. Like now we're saying, what about what if we start looking at continuous sums underneath entire curves? What if we look at the accumulated effect of a curve throughout some region of space or time? That's called an integral. So now we're going to the other side of the calculus coin, and that's really what's happening when we define something like work. So, okay, so I'm going to keep going. So, but work in its simplest manifestation is force times displacement. It's how much. So if you push the block with a force of 5 newtons for 3 meters, then you did 15 joules of work on the block, and that quantity, that measurement is going to start having impact on our physics life. But before it has impact on our life, let me start making the example a little. Let me lessen lower the simplifications on this example. Um, okay, right. Okay. So now I'm still assuming small displacements right now. Oh, sorry. Okay, good luck. Good luck, direct chat person. Awesome. Thank you. Very responsible of you. Okay. I don't mean good luck, power to you. Okay, okay. So now remember there's two assumptions that I'm making here as I introduce this definition. One assumption that I'm making is that the displacements are small, that the displacement we're talking about is small. I'm still keeping that assumption, but I'm relaxing the other assumption. I'm saying, all right, what if the force does not act parallel to the displacement? Well, in other words, what if there's an angle between the force and the axis along which the displacement is happening? In this case, we're calling it like an x-axis, right? Well, what I want to argue is sort of like what we've been arguing all along, Galileo's principle of relativity. The laws of physics occur independently on each axis, even when they occur simultaneously. So if you want to do work on an object, if you're pushing or pulling it so that it traverses a space, the reason we started with the example that we did is that I'm going to say only forces that actually do act on the axis of displacement actually do work. That's why I started with that example. So if you're on some kind of angle, I just want to say it's only the component of your force that is parallel to the displacement that does work. The rest of your force is in effect wasted, or certainly not, or maybe going to other effects, but it's not contributing to this work product. Oh, and by the way, sorry, just to be clear, the work therefore is a product, right? I'm saying work is force times displacement. I mean, that's a simple, but notice that's multiplication. Like it's not division and it's not subtraction. Meaning, if either of the two quantities gets bigger, then the whole quantity gets bigger, right? Okay. But also, if one of the two quantities is zero, then there is no product. That's on purpose. So you could push as hard as you want on a wall, but you're not doing work on the wall, not in the physics sense, right? If the wall doesn't move. So if you want to be Englishy about it, sort of like work is kind of like interaction and result. It's how much you interact with another object and successfully change the state of that object, or specifically the position of that object. That's what work is. It's not just the interaction or the effort, if you like, but it's also the result, all combined into one product. Okay, now I'm saying, well, if you're trying to change the horizontal position of an object, then only the horizontal component of your force contributes to that. Only that matters. So only the component of force parallel to displacement um, contributes to work. And vice versa, meaning, so sorry, so what my handwriting says is only the component of force parallel to displacement contributes to work. And vice versa, meaning you could look at it the other way around. You could say only the component of displacement that's parallel to the force yields work, right? In other words, you set up a coordinate system. This is kind of why we were obsessing over the inclined plane to really make sure we get this idea. You set up a coordinate system. Say my coordinate system looks like this. Say I've set up my principal axis to line up with the direction of expected displacement, as we sort of did in the lab, right? And so this is y and that's x. Then I'm saying only matching components will contribute to work. So however we look at it, this would be true. So if I'm pushing down and to the right, that means I'm pushing somewhat down and somewhat right, right? Or sorry, I guess it'd be more instructive to do this. Sorry. I'll zoom in. Yes. And the whole force was known as F. Okay. So in this case, what I'm saying is I would only multiply F cosine theta times delta X, right? I'm saying I'll just draw the example. Okay, what I'm saying in this case, it would be F cosine theta delta X, or you could just easily say if you turn your head and you picked another coordinate system, you could say F delta x times cosine theta. You could pick the cosine theta of the delta. Like in other words, if you oriented your coordinate system to match, if you oriented your x-axis to line up with the f, then the f would be fine, but the delta x would have two components, and the one that would line up with the f would be delta x cosine theta. Now, I'm not recommending that. But I am saying, notice they would be the equivalent result as they should be in physics, and this leads to a generalization in a way. I want you to notice before I go on, I'm looking, and this is something very important for next semester for what it's worth. I mean, for Physics 204 for what it's worth, is that what's happening here. Okay, all I'm saying so far is work is force times distance, right? But now I'm adding the modification that if the force and the displacement are not lined up, we only take the extent to which they're lined up and multiplied together. So, in fact, maybe, well, I'll say this numerically. Maybe you should write these numbers down. Like if it was all the same example as before, 5 newtons and 3 meters, or the other way around. But if, say, the angle was 60 degrees, right? Then it would be 5 times 3 times cosine of 60 degrees. Cosine of 60 is 1/2. Okay, thank you for letting me know. Different direct chat person got you. Thank you. Appreciate it. No worries. Um, 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 in the other example, it was like 5 times 3, 15 joules of work. In this example, if you were putting at an angle of 60 degrees, pushing at an angle of 60 degrees, it would be like half as much work. It would be like 7.5 joules, right? What we're saying is, you're pushing just as hard, but but by pushing at an angle, you're pushing to some extent down and to some extent over. Only the extent to which you're pushing over like matters to the work calculation or to the overall effect on the box is displacement. So we're taking into account the direction of each one of these, the force and the displacement. We're really treating the force and the displacement each as a vector, and we're multiplying two vectors together. But what we're getting at the end is a scalar. We're getting something like 15 joules or 7.5 joules. That is just an amount. Um, We're not saying 15 joules to the right or 15 joules to the left or up or down. Like by getting rid of the angle, by taking the cosine of it, by oh by taking the cosine, we're forcing ourselves to treat the amount of force and the amount of displacement as though they were just two numbers on a number line, right? And that's why we're getting a lower number at the end. Like we're not multiplying 5 by 3 here. We're multiplying 5 cosine theta, 5 cosine 60 by 3. So we're multiplying a leg of the triangle that's smaller than the hypotenuse. We're only multiplying what some people might call the projection of the force onto the x-axis, like the shadow that this would cast if you put light above it. It's the shadow that it would cast on the x-axis, right? That's shorter than the thing itself. Where am I going with this? I'm saying that cosine tricks allows us to treat the two numbers, the force number and the displacement number, as though they were numbers on one number line. And so at the end of the day, we get a number. We get a scalar. So this type of multiplication, when you multiply two vectors together, but you get a scalar, this is one of a number of different ways to multiply vectors together. This What I'm trying to say, I'm a little bit dragging this out because I'm saying we've just stumbled on a new like math idea. I mean, maybe some of you have seen it, but but I'm not assuming that you've seen it. I'm telling you right now that if you, well, I'll say quick, there's three different ways to do multiplication when vectors are involved. Okay. One way is vector by a scalar. That means you're making an arrow larger or smaller by some amount. So you always get an arrow when you do that. Okay, so there's vector by scalar multiplication. That always produces a vector. But then you can have two vectors, and you can multiply them in a way that produces a scalar, or it turns out you can multiply them in a way that produces a vector. And we'll need that for physics 204. Right now, so I'm just giving you the big picture. Okay, but right now, what I'm saying is when you multiply two vectors in a manner that produces a scalar, the way you can get away with that, or the way we do that, is we only count the extent to which the two vectors are lined up. That's a way of sort of getting rid of the vector issue. But it, comes at a cost is that we get like a smaller number. But um, so when we do the scalar product of two vectors, it's ultimately called the dot product because it's signified with a dot. I'm going to show you right now. And it always is a measurement of parallelism. In other words, always in general, for two vectors, the dot product of some vector A, like the scalar product of A with B is designated A vector dot B vector. And what it always equals is the magnitude of A times the magnitude of B times the cosine. Well, okay. That's true what I just wrote. I probably should have, hold on a second. I'm sorry. Let me give you a diagram just so you see what I'm talking about. I'm saying in general, if you have two vectors, vector A, two arbitrary vectors, and vector B. So like they're different directions, different lengths, right? And if they're separated by the acute angle theta, right, then the dot product of A by B is the length of one times the length of the other times the cosine of the angle between them. And it is always cosine. Like I was trying to show you in the last example how it was cosine in the last example. But as long as theta means the angle between the two axes, so to speak, then it's always the cosine that we're talking about. And the reason, and this is something you really want to get used to, it's totally the same reason as I was arguing last week about the inclined plane. That is sine super cosine confusing or cosine counterintuitive. Sine is super in that the sine of zero is zero. Like, however you want to memorize, like, if you want a memorizer in math and physics, that's a memorizer. The sine of zero is zero, as opposed to cosine, which is more confusing or more counterintuitive. The cosine of zero is one, right? And I know you all know that one is one and the other is the other, but keep straight by just always going back to it's the sine of zero that is zero. So, therefore, as an angle gets bigger and bigger, the cosine gets smaller and smaller. So if you really think about it, I never thought about it this way before until I did. But cosine is really measuring parallelism, right? Because if two vectors are perfectly parallel, if the angle between them is zero, then cosine returns 100% of whatever precedes it. Right. But as the angle gets bigger and bigger, the cosine gets smaller and smaller. We're getting less and less parallel, all the way to the extreme case where if the vectors were totally perpendicular, the dot product between the two would be zero. You see what I'm saying? Is there in other words, right? Um, so right now I'm saying, so this is a thing in general. The dot product, I'm saying two things at the same time, really, about the math. The math is, oh, thank you. Direct chat person, and there's only one of you right now. That means a lot to me, coming from you in particular. We should talk someday. No, I appreciate it. I really appreciate it. And I'm sorry you don't have an exam back yet, but you will. I'm sorry. Okay. No, I appreciate the feedback. I'm glad that's okay. Um, um, but I mean it. Like the okay, okay. Yeah. So this is now a general result that and apparently at least one person here sees, like the general. Okay, this is a general result that we need in physics 204 for sure. We need in all kinds of other vector contexts. I'm saying in general from now on, the scalar product between two vectors, the scalar product, the way of multiplying two vectors together in a manner that just spits out a pure number, only takes into account the components of those two vectors that are parallel. Okay, and the classic example of it, now back to physics, is the example of work. Because we think like if something is being shoved horizontal, in along some axis, only the component of the shove along that axis like matters to. So back to thus. Okay, so thus I'm saying so far, if we're talking about a small displacement, looking at the time, okay, for a small displacement, the amount of work that's done by some force over a small displacement is the force vector dotted with the displacement vector. This is now a strict definition, but bear with me here. I mean, stay with me. It's a strict definition in that I put deltas on it. Like, like strictly speaking, work is the dot product of force with displacement, which, by the way, for any of you that I am losing at all, I am saying I'm saying work then from now on you could think of as force magnitude times displacement magnitude times the cosine of the angle between them. As long as you're literally like sometimes what that angle is, you have to think about. Sorry. Like, sometimes you have to do geometry to see what the theta is. But as long as you understand that the theta means the acute angle between the tails of the force vector in the displacement vector, then certainly this always works. In other words, it always is cosine. So I'm saying right now that work is always the force magnitude times the displacement times the cosine. I just did it again, but you get the point. Um, of the angle between them. And that's a strict definition, not squiggly anymore, as long as I keep the deltas on it. Now, the delta, right? You see, I see delta X and delta W. Why am I doing that? And you may want to write this in your notes. Like for all, like delta, whenever I use delta in math or physics, I mean, in fact, I'm going to say this in math or physics for any variable. So for any variable, Z, let's say, in general, delta Z ah means a small but finite difference between two values of Z, right? Like this, but I want to make it like sometimes people say delta means change. Sure, but I like to say delta means difference. I mean, same idea, but I think like difference as in subtraction, right? Like so delta, like as in slope. Like I'm saying this is true for any variable at all, is certainly including x or y. Like if you're on a graph and you talk about the slope of the graph is delta y over delta x, right? What are you saying? I mean, what are you really saying? You're really saying when you say delta y over delta x, you really mean like y2 minus y1 over x2 minus x1, right? You're saying the difference between the y values divided by the difference in the x values. And often we're using this when such differences are really small. I'll get to what I mean by small in a second. I mean, obviously, small is relative, but we can use these terms when differences are really small. But no matter how small they are, they're still finite. Whenever we use a delta, we mean there literally is a value for y2, and there literally is a value for y1, and they're different enough that you could actually subtract them. Maybe it's 0.001, but it's a number, right? Right? When we use deltas, we mean even if it's a small difference, it's a finite difference. Now, what you know from calculus what you know from calculus is we switch. Now, you may have thought of this or not. I don't remember if I said this in this class exactly, but when we switch to the letter D, we're still saying difference. When we switch to D, as in dy, dx, and all that stuff in calculus, it's not, it seems so out of nowhere it just seems, I don't know what it seems like to you. To me, it all just seemed like a mess at first. But what I'm here to argue is that when we switch to a D, we're just trying to capture exactly what we ever meant by delta, only we're now going to the so small that it's infinitely small case. Like dz means delta z. It just means a difference between two values of z. However, sorry, I just wrote it wrong. Well, however, in the limit as delta z goes to zero. That's what dz literally means, right? I.e., dy equals the limit as delta y goes to zero of delta y, and dx means the limit of delta x of delta, right? So, like, I please note if you calculus wise, and I'm watching the time. Okay, I'm gonna say I'm watching the time. I don't want to rabbit hole, but like that thing that down at the bottom that you see, definition of derivative, hugely important, right? I know you've seen it a million times, at least in Calculus 1. If you're like me, and I hate to always say that, but when I memorized that, I did what you did. I memorized it, I used it when I was supposed to, but it didn't, it just was a bunch of gobbledygook to me. You probably are ahead of me in this regard. Just to be clear, in case any of you still thinks it's a bunch of gobbledygook, that very last line of the board, what I'm trying to say is it's just saying that the dy dx, the derivative, is slope taken to the limit. It's rise over run in the limiting case where the run is being shrunk to zero, right? I mean, like literally the top part just means y2 minus y1 if you think about it. And the bottom part just means x2 minus x1. But in the okay, so I can't so what I'm saying is so I'm saying derivative, it's not a derivative is not dy, a derivative is not dx. Those are each called differentials. A, they are just infinitely small differences. A derivative is a ratio of differentials. It's an infinitely small rise that you get when you walk on the graph an infinitely small run. Now, why am I saying all of this with only 20 minutes left? Like, in principle, that's just I'm not saying we're about to redo derivatives. I am saying that we're going to reuse a differential. I am trying to remind you that a d bleh, is just delta bleh, taken to the like a really small delta, an infinitely small delta. That's all the d ever means. So, Well, okay. So what I'm now about to do is relax the other of the two simplifying assumptions I'm making behind the definition of work. Work is this force times displacement, parallel components. But I keep saying that's the definition of it as long as the displacement is small. So what's that all about? Why am I? And I keep designating the small displacement, the small but finite displacement with a delta x. Why I keep saying that is I that definition is fine as long as the delta x is small enough to allow for just one value of v. As long as delta x must be sufficiently small to prevent f from varying, right? Like I'm just on like if you're pushing a box through some displacement, as long as the displacement is small enough that you don't have the space or the time to change up your f, as long as you're pushing with basically a constant f, or you're soon going to change your f, but we stop measuring the displacement before you do, then there's no math problem and there's no physics problem. Just take whatever that number of newtons is, multiply it by the delta x cosine, and you're done. That's why this definition this definition works as long as there's deltas in it, as long as we're talking about a small amount. What if there's a big amount though? What if the displacement is big enough that F has room to vary, right? If F is big enough that F varies, if F is not a constant, then the total amount of work, the total amount of work we do must be the sum of all of the constituent works, just meaning this. And yes, that's a sum, sigma sum. Like, don't be intimidated. I mean, you can be, but you don't need to be. I'm saying, I'm saying if work is force times displacement, that is fine as long as we have a force number to work with, right? So say the force is changing every meter, right? Say in the first meter, the force is 1 Newton. Then in the next meter, the force is 2 Newtons. Then in the next meter, the force is 3 Newtons, etc., right? Then that seemed to be a problem for our equation, but we could go piecewise. As long as we believe that the whole is equal to the sum of its parts, which we do here, then the total amount of work you would do throughout this varying force would be the force times displacement for the first meter plus. So you follow the sigma notation, like you set the index, the counter to 1. Don't be intimidated, and you say, okay. And in fact, let's even make this. You set the counter to 1. You look at the first force that corresponds to the first meter, multiply them together, um, put them in your bag, then up the counter. So go to the next meter, ask what the force is there, multiply them together, put it in your bag, and go all the way up to the last meter, the meter number n. And you have the total amount of work. We're just saying the whole work is equal to the sum of its parts, right? Total amount of work, if the force varies, would equal the sum of all the smaller works. And stop me if that doesn't make sense. But now, of course, here's the one way it might not make sense. Well, I mean, hopefully it makes sense. I'm just saying the whole is equal to the sum of its parts. But of course, in reality, in macroscopic mechanical reality, in space, it's very unlikely that life looks like a cartoon. It's very unlikely that you're pushing a box with 1 Newton for a meter, and then like you stop, and then like you go to the next meter, and then you like instantaneously double your force to 2 and do that, and then you like it's very unlikely that in real life it's going to be a discontinuous step function, if you see what I'm saying. It's far more likely. What if, sorry, I mean, what if F, right? What if F varies continuously as a function of position, right? Like no matter where you are, the F, like in other words, 1 meter is too small to divide this whole thing into, you're trying to catch the force at a constant value for to do multiplication. So you take the whole trip and you divide it into meters, and you're like, aha, I'll divide it into meters, and each meter I'll use a different F value. But then you look and you're like, even through a meter, the F is varying. So then you divide it into half meters, and you're like, the F is still changing even in half meter. And you go down and you go down. And no matter how far you subdivide it, the F always seems to be changing. Why? Because it's changing in an infinitely divisible way. What do we call that? We call that continuous rather than quantized or rather than discrete, right? I'm saying, yes, if you're thinking calculus is about to come in, you're right. And quick sidebar, when I did all this stuff, and I'm not pulling your, when I say that, like this stuff was hard when I was for like whatever, when I was first doing calculus and physics, and I don't remember but I was smart enough and responsible enough to notice that every freaking time they introduced a theorem in calculus class, they always started with all this about if y is a continuous function of x and blah, continuous function and blah, 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 continuity, but mean value theorem. And I'm not mocking, like it's all very real stuff. But I didn't understand it at the time. I noticed that continuous function always came up, and I was always like, get past the wah 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 and just give me the derivative thing, right? But here's why: continuous just means infinitely divisible. Calculus comes up when infinity comes up. If the function is, I mean, if the force is varying so smoothly that you cannot find an interval small enough to capture a constant force, then the only way to do this, right? Then what we need to do to calculate the full work over a full interval, then the full work, if the function is continuous, if the force is varying smoothly as a function of displacement, then work would be that sum that I wrote down a second ago, but in the limit, right? It would be. So what I'm saying is what we want. I'm not saying how to do it yet, but I'm just saying what we want to calculate work in the general, in the most general context of physics. What we want is to take a step of displacement, ask what is the force, what's the horizontal, whatever, what's the matching component of the force for that step. So I take a step of meters, multiply it by the newtons, put it in my bag, then take the next step, do the dot product, multiply the newtons by the meter, put it in my bag, take the next step. But if I really want to catch all of the products, if I don't want to miss anything, I want to take this concept, I want to do this in the limit as each one of my steps approaches an arbitrarily small amount, an infinite. I want the steps to be infinitely small. You see where I'm going with this, right? In other words, if I were graphing f as a function of x, if f was doing some weird smooth continuous thing, I want to be taking steps along the x-axis, and at each step asking what the force height is on this graph, right? And you see where I'm going. And I want to be multiplying the displacements by the forces, but in the limit. So I want to be getting the areas of those little rectangles, but I want to do it in the limit as the rectangles are shrinking to infinitesimal width, right? I'm not doing it to make myself math happy. I mean, of course, I am making myself mad, but I'm doing it because that's what I need. If I want to calculate the total accumulated effect of force throughout some space, and I want to account for the very strong realistic possibility that the force is varying smoothly throughout that space, what I want is the area under the curve of the X graph. I want the limit as delta X approaches zero of that sum. And you know the name for that. But what you might not have known is like why it all works like this or what it meant. What I'm saying is the limit of a continuous sum is, of course, called an integral. And look, I'm saying I never knew this until I did of what I'm about to say. I'm saying that the sign for an integral, first of all, it's an S. I never knew that. You may know that. But I mean, it's just an elongated S. It stands for sum. Okay. The integral sign is what happens when you smooth out the jagged, intimidating, discrete sigma, Greek letter sigma up above. That also stands for sum. Sigma is what we use when we're adding up things piece by piece. And specifically, often we use it when we're adding up little products. Products of what? The dependent variable multiplied by the independent variable. Like that's all it is, F and X. F depends on X. Force displacement. So when we're adding up a bunch of products, we call that a sum. But if we go to the limit, and that would be a bunch of rectangles underneath an F curve, but it would be a bunch of rectangles. If we go to the limit where the width of each of those rectangles is infinitely small, then we're smoothing out that sum. And the delta x gets replaced by a dx. So I'm saying a number of things here with 8 minutes left. First of all, let me make this super legible, or as legible as I get. I'm saying the proper definition of work in physics, the work that you would do to push a box from location X1 to location X2, the work you would do is the integral of the dot product of the force and displacement vectors. This all assumes that F itself is a function of X. Okay? So the work you would do is the integral of F with respect to dx, which just means, well, first of all, it means anything you know about integrals, how to do them, now applies. Okay, including when you're going to do the homework. Now, by the way, I've just given you a lot of information here. I'm going to give you one more key piece of information that you do need for the homework. Then you're going to find that a lot of the homework is more exercisey and simple than this. Like the truth of the matter is, you don't even have to deal too much with the calculus yet in tonight's homework. What you mainly are dealing with in tonight's homework or whatever, the homework that's due Wednesday, mainly you're just dealing with the idea that work is force times displacement. Okay, this is all sort of getting you ahead, not behind. Um, but but I'm trying to show you that an integral is something that actually made sense from the get-go. Even if you've just been memorizing integrals or thinking of them somehow as antiderivatives or something, the way to solve an integral is to understand about doing derivatives backwards. But what an integral is, what it means, why it ever comes up in our life, is an integral, and please write this down if you're still with me. An integral is a continuous sum of products. What products? Always the dependent variable multiplied by the independent variable. Always. In other words, that dx that should I say that again? The integral is the continuous sum of products. The product is always the dependent variable multiplied by the independent variable, like whatever we're talking about. The reason there's always a D something in your integrals that you do in calculus class, it's not just a bookkeeping thing or just like a math teacher thing or something like that. Literally, it's what's happening. It's why we think of them as the area under the curve when we're thinking about graphs. It's that you're always in an integral. You're always walking along the x-axis. You're always taking steps along whatever the independent variable axis is. And by the way, in this case, in physics, it literally is space. Like this is like there, I'm really trying to say, I am watching the clock, I promise. I'm really trying to say, I'm not, well, partly to some of you, I'm saying if you feel like you've understood integrals till now, then think of work as an integral of a dot product. It's technically called a path integral. If you understand integrals already, then think of work as you're walking along an x-axis of space, and as you're going, you're accumulating how much the dot product of force is. Like, what's the dot product of the force with me right now? What's the dot product of the force with me right now? What's the dot product of the force with me right now? And you're adding it all up. Okay, that's what I'm saying work is. It is the most fundamental, simple case in actual space that anybody could imagine of what an integral would look like. Work is the integral along a path of force. But on the other hand, and there's still 5 minutes. On the other hand, don't leave me because I'm talking calculus now, and you're like, yeah, yeah, calculus, wah, wah, wah. Like I can respect and empathize with that, but I'm here to tell you, no, now go the other way. I'm saying if you were with me for 60% of this discussion about what work is, that we're just like multiplying, like how hard you're pushing the box by how far it's going. And we're doing that because we want to look at the accumulated effect of your force over space. Then I'm saying if you ever never did think you understood what integrals were before, or you just memorized how to do them, but you didn't know what they were, this is what they are. An integral. So whether the calculus helps you with the physics or the physics helps you with the calculus, like welcome to my world. It just goes, it will get better and better as they feed off each other. The integral is the continuous sum of products. The classic integral is the work integral. Here it is. And now that's what it is. So work is defined to be the path integral of force. Okay, that covers all the cases, whether big displacement, whether parallel or not, like that covers all the cases. But now, why do we care? And how do you do the homework or whatever? The effect of this, really quickly. In other words, what's the double equal sign? What is, what is, come on, come on, come on. I know we have 3 minutes. Really? Really? Bored? Hold on. Pause. Okay. What is the, what is like what does work do? When you do work on a box or on any kind of mass, I'll really quickly look at limiting case. If you add up all the forces, I'm just going to the limiting case just to make a point. If you add up all the forces acting through a displacement, well, we know that F net equals MA. Right? And from kinematics, if we're only like, I want to make a substitution for A here. I have 2 minutes left. I don't care about time. This is all about space, forces acting through space. So I'm going to use the one equation for A that doesn't have anything to do with time. Well, oh my God, when my board just, sorry. Continue. I'm saying, well, A is V. You can look this back up from your midterm or whatever. A, that's one equation for A. We have 1 minute. So I'm going to substitute in and say delta F equals M V squared minus V naught squared over 2x, but that's all multiplied by x. So the x's cancel. And what that means is that when very quickly, I'm saying that when you do work on an object, it's 12:04, and I'll stop in 1 minute. That's all I'm writing. When you add up all the forces doing work on an object, the net amount of work on the object changes the 1/2 mv squared of that object from some old value to some new value. It creates a different, and so we give a name to that 1/2 mv squared thing. We call that kinetic energy. And we'll talk more about this on Wednesday. But what we're saying is when you do work on an object, you give it more 1/2 mv squared. If you do positive work on an object, you give it more 1/2 mv squared. When you do negative work on an object, when you push against the way it's going, you take away 1/2 mv squared. What is 1/2 mv squared? Well, it's just what's spat out by the math, but we give it a name. We call it kinetic energy. What's the point of kinetic energy? The more you have of it, the more work you can do. Energy is like money. Work is like a transaction. A transaction is a passing of money from one party to another. The point of money is the ability to do transactions. So work is the transfer of kinetic energy. Kinetic energy is 1F mv squared. That was a lot. Um, I'll be loose about the homework, but you know what to do. All right, and I will keep coming with your exams, and I'll see you Wednesday. Thank you. Bye. Yes, bye. Bye. Yes, have a good day. Sorry. Bye,